And we are, and Vikas is coming in. Hey, Vikas, good to have you. Uh, Good afternoon, everyone. And let's start with Shaunak. So, Shaunak, maybe you wanna share your screen or see
Yeah.
how you go.
Okay.
All right.
Okay. Do you see IDL?
I do. Yes.
Okay. So here I've opened all the routines here. And actually I have all the files now in the directory.
In the
so
same directory. Okay.
Yeah. So the main question is how exactly to run these routines using the IDL commands.
How to do what?
How to run these routines using IDL commands.
Oh, if you yours is the configuration of yours is slightly different from mine. But if you highlight one of the routines, uh, you should have a button there that is for running. I can't see it. Okay, but if you go in the command line, if you do .r and the name of routine, it should go. If you are in the same directory of the routine.
So like
In the command
I could
line,
try bailing. Right, I could .r.
yeah, .r space and the name, it should go through.
So
Error compiling. It's not finding. Are you in the same directory where the routine have been created? If not, you have to end in the. Oh, there you go. Run. See that run over there on the very
right
command.
here. Oh.
Yeah.
Run. Okay, compile.
And then you have a compiler. Yeah. Okay, that should be in. But you can set your path. If you go to File, see if I remember, File, and then Preferences. Yes, and then you can set a direct tree to the place where your routines are.
Oh, okay. So wherever I've stored these libraries.
Yes, yeah. So if you tell this path where all your pro routines are, so when you compile the routine or .run the name of routine, it should go through.
Okay, so it seems I've compiled them in the
In fact, you don't need even to compile. If the routine have been tested, that's the whole point. If they have been tested, so you compiled previously, there are no bugs, no nothing. So once you call them, IDL go to all the possible directories and subdirectories that you have been assigned as having pro routines and try to find them. And if you find it, compile that one and then execute if you have some execution to go.
Mm-hmm. Okay, so I could put all of this in one directory, right? So if I put the TW folder in my IDL directory.
I wouldn't. I would put your, for instance, think about projects. So in IDL, you have a bunch of library that you're going to be using on and on and on, like the one to do cross correlation, the one to do polynomial feeding, or you name it. So all these routines that have been developed by somebody else and is part of one of the library we have installed should be in your path. So that's one thing. The other thing is, let's say we have a project now that is to understand how TW Hydra works. And then we create a subdirectory that has some routines that we sort of a disposable. They are good for that particular project. And if we want to use them for something else, we have to tweak them. So then you can create a subdirectory and then load all these routines somewhere. It could be in your document tree, you know. So you open your document, and then you can create. Okay, in the document you have all kind of things. You have your classes. You have I don't know. You have your to-do list for the week. You have shopping list. I don't know. And then you can create one called ideal projects, something like that. And then in ideal project, you open another one that is TW Hider. And then in that one, you can have all your routines, you can have your files, you can have your data, you can have your dots save file, you can have your veiling calculations, you can have all kind of things.
Okay, so would you recommend that I just create a folder of ideal projects, put the TW Hydra one in there, and then add this to the preferences to the path here?
Yes, and then you could set the preference to ideal project.
Okay.
Because then from there, it would try to find everything that is under it. And it should work.
So, okay. Okay. Is there any need to put any of these libraries inside the ideal project?
I'm sorry, say it again?
Since these libraries contain certain routines, should I put these folders in the ideal projects folder as well?
No, Astron is a library. Coyote is also a library. Process is also a library. So all of those three that I can see there, I would put them, and you have a double process. So I don't know. Oh, probably one is
that is it.
Yeah, collapsed. I would put this library in one ideal library directory. Those are important library, and they should be in your it should be in your path.
Okay, and now ideal project. So I just need to add that to the path.
Yeah.
I think that should do it, right?
It should do, I think. Yeah.
Yeah.
I'm not a wizard with computer, but Ognian is a wizard. Vikas is a wizard. They should let us know if something is not right.
What do you think, Ognian?
So the way to know, just call one of the routines and see if the system is alive.
So I was looking at something else. I was hoping that you guys you're gonna resolve it. Let's go once again. So Shona, could you please let me know once again what's the issue?
Okay, so here I have. So I just need to my ideal project directory as one of the path preferences, and so that's basically what I did here. I have a directory called ideal projects, which will contain folders such as the TW Hydra one. And in addition to these libraries above here, it'll also add the projects to the path preferences.
So, and what is complaining about IC? Oh, I see error opening veiling pro. And after that, it was opened and compiled. And what is the further problem? What you were
in the beginning, he was compiled veiling, but the IDL was not rooted in the directory where the routine was located, and then didn't find it. And now he should be able to. So I would say if you do that, you should go through. Yeah, there you go.
Yeah, now it works.
So he found it. So let's say later on, if you decided to make a project in your school using IDL library, and then you open another project, and then you just make sure the path finds it.
I believe that this library is looking for compiled projects. So, and the one and only thing what I'm kind of afraid what might have happened, if you put too many too many paths, we can get conflicting. It can find it on two places at the same time, and it can complain about that. So, so far I see that it compiles the veiling. That means, let's see the next step.
Yeah, should be fine. Yeah.
Can you compile entire directories?
You can.
Okay.
But I don't think IDL does that because you would invest a lot of time. I think it. I don't know how it does, but you just need to find a routine. Now, Ogni is right. If you have, for instance, a project in TW Hydra and call veiling, and have a veiling that does the job, and then later on you work with another star that has some variability you're interested, and then you have another veiling routine in that sub-project doing things, and then IDL will compile the first one that finds in the search.
So bottom line, I will try to put one directory where I keep my quasis, because as Celsius says, if it thinks about if it imports the first file found, that means it is importing something. You are hoping it is going to import for your current directory, but there is another directory you forgot, you clicked to be imported. Yeah. It imported from another place. And that means you are changing something, and you say, wow, why this is not compiling it right? Because it is pulling it from another directory. That's, if you can limit what you are importing, that would be better.
Now, there is one thing that I would like you guys to be aware. I don't know how it appears in your workbench. So if you let me show my workbench, I will try to explain what I mean. Is when you edit a routine that has been compiled and is saved in the disk, and you wanna improve it. So if you release your screen, I will quickly show something here, and then I go back to you.
Okay.
Okay, so for instance, I have this routine here, line flux. So this line flux is saved in my computer. So Hydra. So I have a subdirectory pro that have all these routines. So it's there, right? But let's say I want to tweak a little bit and I want to improve somehow, and I do small changes, right? And then I do these changes, and I compile, and then it's going to be compiling and updating those changes into this compile file. And when I execute, it will execute with those changes. But these changes are not saved directly in the file in my disk. So it's somehow in this module here, in the workbench. So if I want to save it, I want it to specifically save. And then it's going to find the directory it was, and it's going to update it. Does that make sense? Because it happened to me that I made a lot of modification, thinking that automatically the modification was being synced to the disk. It was not. It stays in the workbench.
Alert from Milo.
Okay, you be quiet. Okay. All right. So Shaunak, any other point?
Two questions. One is, does the order of compilation matter?
No.
Okay. And then the other one is, after compiling, what commands do I need to exactly run through in order to?
Okay. So for
I
instance,
need to run through them in a particular order.
No, you. For instance, I wanna measure line flux. So then I have this routine here that I compile. See, my case is different. I have this button here that does this compilation, and the other one that runs. So, but it's compiled, and then I call the routine. So helium 15875. Oops, 5. And then I have to give a record number, so number 1, for instance. And then it's going to complain because I did something wrong. What was it? Helium 158, 5876. And then I have to get out of here. And then so this routine now is working, is doing what's supposed to do. This routine reads files, plot them, and it's right here, and keep waiting for me to do things, which I'm doing now. Okay, and eventually is going to call another routine in the sequence, in the logical sequence of it. It's going to call the other routines that are supposed to be working inside it. Mm-hmm. So you don't need to worry about the order, because the logic of your program will do that for you.
Okay, but which file is a good starting point, or which routine is a good starting point?
Depends on what you want to do. For instance, right now I wanna measure the flux. So then I build this routine here that does the trick, that measure the flux, right? And then it reads the templates, it reads the tutorial, and the reading is done by another routine called get temp tw hydra. Record, wavelength, so on, the Julian date. And then this routine here is going to read the wavelength, the flux of the tutorial, the flux of the template. It's going to bring the Julian date into this program, and then goes in another sequence down here that cuts and slices this big spectra with I don't know, hundreds of thousands of pixels, and putting 3,000 pixels or so. So it's more manageable. And in fact, 1,000 pixels, as I can see here. And then just to reduce, computer time, and then it keeps going down, and then plots. So the plot you are seeing is because the command was inside the routine.
Okay. So ideally, should the routine open the file for you, or should you actually open the file using the command line?
Yes, the routine opens the file for you because you asked the routine to do so, right? Mm-hmm. So this program, Helium 15875, the first routine inside is this one over here, right? So if I look at it, it should be here. Right there. So what this routine does, the only thing it does, it goes to my subdirectory, and I define the subdirectories here. That's the address where my sun spectra is, where my standard is, and where my tutorial is, and then restore them, right? And then take these 3 different spectra and interpolate them so that I have only one wavelength scale for all of them. That's what I'm doing here. I'm just working with one wavelength scale for all the possible flux in sun, T-tori, and template. It's easier to work that way. And then it finish. So, but when it finish, it brings that information into this routine helium-1 5875. And what that routine does is just slice them and then start doing things up to the point that eventually it plots and then ask me to define where the continuum should be passing. Okay, and then the program goes. What you could do when you have a free time again, if I have a free time again, weekend is complicated. I and Shaunak was, okay, can I see you now? No, I'm not in the house. Why not at noon? Well, but no, I can't. It's complicated. But when you find a time that we both can be in computer, maybe you could try to run from your computer the program, and then I can help you be more efficiently and help you. So tomorrow, Monday, I will be home most of the time. So in late afternoon after school, if you want to just jump in, or in the evening, we could try to do the trick.
Okay, I'll let you know.
Okay, wonderful.
Yeah.
Okay, so Philip, I'm passing to you. So let me stop sharing here. Oh, by the way, before I go there, let me. I'm having problem managing these different windows here. Okay. Stop sharing. Okay. Before we go further, I would like to introduce everyone. Sarah Soul. Sarah, do you have a microphone that you can say something?
Yeah.
Okay.
I do.
Yeah. So this is we call ourselves Evergreen Valley College Citizen Science Initiatives. So we are trying to build undergraduate research. Not only for undergraduate students like high schools and community college, but also citizen. So even if you don't want to go to school, you are done, but you want to do research, so that's the way to go. And right now we have just one research going on. We are researching T-tori stars, and we have one star that we are trying to target. It's a TW Hydra. T-tori stars are premium sequence stars. They are still contracting. They have circumstellar disk, and they are wildly magnetic. And there are all kinds of fun things going on. And we went to ESO webpage, and we found 92 files of these star observations since 2002. So we download them, and then we are analyzing the spectrum that goes from about 4,000 angstroms all the way to 9,000 angstroms. So that's where we are. There is a microphone in the background. Anyways, so Shaunak are two high school students, and they initiated this research 3 months or 4 months ago, probably more, maybe, I don't know. And Ognian is a computer wizard helping us in Python. Vikas is also a computer wizard helping us in Python and start getting his hands on T-tori stars. We have Lee Rotter that is not logging right now. He's also a computer wizard. And we have a member in Brazil, Eduardo Ceperuelo, that are also working in premium sequencing stars, but he's not logging now. He's 4 hours ahead. So that's it.
Yeah.
And who are you?
So I am a second-year graduate student right now. I know that I definitely want to do research in astrophysics, but I don't have a lot of research experience at the moment, so this is my opportunity to learn a whole lot of new things and be able to go start applying that to a research project within the next semester or two.
Okay, very good.
So
that's wonderful. That might be some good place for you to hang out for a while.
Mm-hmm. Yeah, I'm looking forward to learning the IDL programming.
Oh yes, you have an IDL account in San Jose State.
Oh,
yeah, and I have in fact, Philip could help you. I have some thing walk in my glasses. Philip could help you to get a license. We have a license that can be reproduced. I don't call it pirate because I'm not pirate. Somebody gave me and said, "Oh, we can use it," so I'm using. And so Philip can help you to get a copy of it.
Yeah, that way I can have something on one of my computers.
There you go. Okay. Okay, Philip, it's all yours.
Okay, so let me share my screen, and I think we can walk through the PDF that I attached in one of my previous emails.
Yeah, I saw your email.
Okay. Can you guys see?
Yeah.
Okay, cool.
Plotting flux gradient. Yeah.
Right. So the source code is actually on my.
Just for Sarah, if you could, veiling, I didn't explain what that is. If you could give a small, quick explanation of somebody could help, that would be good.
Right. So the way I understand it, veiling is a result of gas or in the on the outside of the star altering the spectral signature of a certain element, and then we can calculate flux based on the sort of deviations that it will produce in the spectrum by comparing a template and our observation. And we've been doing that using some of the routines that Celso has sent. And I currently don't have the IDL program, but what this Python program is doing is it's taking a save file that's being produced from one of our IDL programs, and this save file contains information like line flux and Julian date and veiling value, and we're basically plotting the data and looking for a trend that we can analyze. So with the observations that we had, there are 3 clusters, each organized by Julian date. So these were just over a period of consecutive days. So we have one here, and one here. And what I did here in this program was just plot them together and look for relationships.
Philip, when you say here, here, and here, there is nothing showing. No cursor.
Okay.
So I wonder.
Can you guys see my cursor?
I can see your cursor.
Okay, yeah. So when I say here, I mean, for example, in this interval, roughly 5,400 in Julian date, there's one cluster of consecutive observations.
Where I don't see it.
Yeah, I don't see the graphics. Can you go?
I don't see the graphic either.
Huh. On my screen, the can you guys see this PDF here?
We see the first page.
I have one page.
Let me try sharing my screen again.
Yes, I think you are sharing only one of the screen, maybe.
Maybe.
But not the whole thing.
Just a second. Okay, can you guys see now?
Oh, yes. Yeah. Now the universe makes sense.
Okay, yeah, sorry about that.
So we see everything.
Yeah, so right here, we're basically plotting this data from the IDL program. And so we have 3 clusters of data. here 5,400.
Philip, just for Sarah, because and probably Vikas too. So the IDL program you mean is a program that is measuring the emission flux of helium line, right?
Right.
So you did that independently prior to produce these plots.
Right. That's correct.
Yeah. Okay.
So if you'll just give me a moment to set up the IDL program so I can just give an idea of like a sample output. I have it on an SSD that
okay.
I don't have with right now.
Sounds good. Go for it.
Okay. I'll be right back.
But also for Sarah. So if you look this in the X scale, you guys can't see my cursor, right? Because I can see, I can move a cursor here.
Yeah, we see your cursor.
Oh, you can see it? That's
we're moving something.
I'm moving, yeah, that's amazing. So I'm doing something that is affecting Philip's computer. That makes no sense.
I think that was just me moving the...
No, I'm moving circles here. No, that's me. Or we have some synchronicity.
Guys,
brain
I
to
think
brain.
aliens are trying to interfere in our research. I mean, they don't like it because we are seeing that.
But this number is in the horizontal scale is Julian date. Oh, now the ideal is coming. So you can see those chunk of data means that in this season here, whoever observed the star got a bunch of observation, but it didn't in the following days. And then we have a big period here, probably a few years, I don't know, without data, and then it comes again and it comes again. So we would try to do the best we can and try to learn the variable behavior of this star, looking both on the long range of 15 years or so, and also in the short range, if we can see how the star is changing its line flux and emission in continuum flux overnight, night to night. Okay, go on.
Right, so I'm just setting up the IDL program right now so I can show sample execution and the kind of file that we're producing. So I'm just opening up the helium 15875 procedure right now.
We don't see the IDL stuff.
Yeah, I know, it's in my other window. Okay. I can move it over here if you guys would prefer.
So that's actually...
Okay, so that is the IDL.
Okay. And then I'll run with, say, record number 92, for example. And these records are being taken from a directory here. It's called Save Files. And these contain a spectrum. This is an observation of the TW highest spectrum. And when we run the program itself.
Sorry for interrupting you. These are ESO observations which are taken from the website by Celso, right?
I'm sorry, say it again.
So the TW what view is showing these are the observations which are taken from the ISO site by you and Ali.
Yeah. It's public domain. I mean, that's the point we are trying to do. We are in astronomy specifically, you have so much data out there that because of technology now, if you want to observe some little thing in a system, because of technology, you ended up having a lot of information that you don't care for. And then you have to publish, you have some prerogative to do whatever you want to do with the data for, let's say, 6 months or 1 year. After that, it's public domain. So we are trying to take advantage of that and just wait data to be available. And if we have the skills to do research on certain line of research, just go ahead and do it. Okay, go on.
So just probably for Sarah and Vikas, and Celso has written software which exists for pretty long time. I mean, and here from this, for each graph, it is, I mean, spectrum. It is possible to compute the flux. It is possible to compute the value.
Yes.
This is for each and every from these 92 files what we have, and this is with that program what Celsius has written. We are saving in save files for each and every spectrum, 92 of them, veiling and flux. And then with the Python, what Philip was showing, we are just plotting together his findings, his results.
Yeah.
Phil will do the rest. Phil, you can take over. Sorry for interrupting.
No worries. So in this ideal program, so this procedure, we're plotting a spectrum using an interpolation function. So this is the continuum. And these lines, I believe this might be an outlier.
This is junk. Yeah, this spike over here is. Can you see my cursor?
No, we can't. Can you give what angstrom?
Oh, okay. It's you have in pixels, so you have a spike at about 50, pixel number 50. Yeah, that one.
Right.
This is junk, and you have another one at 300. 300. Yeah, that's junk, and 350. That's junk. So the helium line we are interested is the one Philip is showing now. Yeah.
Yeah, so we've plotted our continuum, and this is the observation. And then when we go to the template, which is here, we're also going to plot another continuum so that we can compare the template and the observation. So again, we're using an interpolation function. And I'm going here because, if I remember correctly, here is an absorption line, or the beginning of an absorption line.
Yeah.
Right, Celso?
Yeah, helium. Oh, not helium. The sodium lines, the same transition that makes San Jose streets kind of a yellowish.
Yeah. So then we are extending the continuum here, and now we have the we are.
Well, the vein is good.
Value.
The vein was good.
Yeah, so it actually did turn out pretty well, so we don't really need to make an adjustment. I believe actually we can keep it as it is. And now we're computing the line flux. So that is the integral of this interval of the helium emission line. So I can choose an interval. So here and here, for example, this would be a good range. And then we click the bottom to save it. And so,
Philip, can you go back to the other? Okay, I would put this line a little bit above. Yeah,
okay.
yeah. The reason is, see, the continuum on the helium, on the TW Hydra, which is the white line,
I see.
Is more above. So you are adding some extra there.
Okay. Would it be better to go back and recalculate, or?
Oh no! I mean, you're just demonstrating. We have to do all of. Now we have 175 files.
Right.
So, but just go on.
Yeah. And so now we get the flux. So if we open up the line flux program here, which is being called at this line, so line flux, we're getting this VRET array, and that contains the flux, which is the integral we just computed, the equivalent width of the emission line, and then the center x-coordinate of the emission line. And so this is useful because this is what we're plotting in the Python program. This is the flux we're referring to. And we also have the Julian date stored along with that, and the veiling.
Okay.
So here in the Python program, we're importing all the libraries, and now we're plotting the information that we obtained from this program. And
Philip, can you show me the line flux routine you just?
Yeah.
That is the line flux. Oh, I see. So it comes out of it, And then VRET comes out, and then the other one is the one who's saved. Okay.
Yeah.
Yeah. So
I have kind of a general question. So I just I've been looking, kind of looking more at some of the graphs that we're seeing.
yes.
We're looking at a single time frame for each of these, and we're not. It's like over time we're just plotting the flux itself, but then when we're trying to identify things like the helium line, what window are we looking for that? What time window do we figure for that?
Each observation, each save file, this is the spectrum, is a single observation, and this is the timestamp. Could you please show once again the spectrum from IDL, if it is available? Yeah, this is a time. This is for example, 21st of January 2003, that timestamp. And each of these files, they have a timestamp. And each save file, what Phil was talking about, represents the integral. I mean, the flux. This is the area which is above the line here. This is one number. The other number is the computed value. And this is that means from this spectrum, it is losses, and from this spectrum we get three values. One, it is the width of the first parameter. The second was the vector, and the third parameter is the area of the here. That's it. So what we are getting, that is, so your observation is correct. We have one timestamp for three parameters produced from this graph.
Oh, okay, I see.
Yeah.
Okay, that makes, okay, I think I got
Point
that.
represents, for example, on the each point here, the red guy, each point represents the third parameter. Yeah? And if you go a little bit lower to show blue, and that means we measure from these three parameters together. These are the ones who, this is the red is the flux, and the middle is the vein.
Oh, okay, got it. And I guess one question, so I just finished reading a paper. Are we doing the data from not the CSO, but the All Sky Automated Survey?
I'm sorry, which survey?
The ASAS, All Sky Automated Survey?
No, this is a different survey. I mean, this data was collected by, I don't know, by few researchers over the time.
Okay. So it's pieced together from a lot of different...
yes. So the ESO has a lot of telescopes, and each telescope has a lot of instruments. So when the law of the land is when you request telescope time and it's given to you, you have proprietary time for 1 year. I think that's what it is. And then after that, it's public domain. So anybody can do anything with the data. So so if you go to ESO, and there is a portal that allows you to determine which data you want from which telescope and from whatever instrument you want. And then when you ask for the data, it gives you the data of the target you want that we're taking since 2001. I think that's what it is. And then let you know which one is available, which one is not. And then if it's available, if you want it, just request, and they send it to you, and you have to download it.
Okay, that's great. Oh, that makes sense. Okay,
yeah,
cool.
it's great. All right, Philip, go on.
Yeah.
Mm-hmm. Right. So what was interesting about what we found was that there was a proportionality between flux and veiling. So if we look at this plot, for instance, in this cluster of observations near 5,400 Julian date, there is a very rough similar distribution here. It's not really visible since it's a wide range of Julian dates.
Right.
If we go to a smaller interval, so for example, record 3 to record 23, it's a slightly more visible proportionality. So for example, here, this data point, we can kind of see this curve going up, and we can see these 2 points are slightly similar to here.
Right.
And they're distributed fairly similarly.
Right.
And again, we have another interval, 51 to 57. There's a pretty similar pattern. I think this might be an outlier, but here is fairly similar. These two are fairly similar. And again, record 70 to 91. There was also some similarity. So to test this, I made a linear regression line comparing flux and veiling, and there does appear to be a relationship between them, since we had a standard error of 53.8%.
Yeah, 53%.
There is some. It's fairly accurate, and it appears to be some proportionality.
Quick question on the regression. Did you get a measure?
I'm sorry, I didn't hear the last bit.
There is a background sound. What we could do is we all have our phones mute, and then we liberate the phone when we want to say something, just to avoid the background.
Yeah, that would be great.
Okay, go on.
Okay, sorry. Real quick. So, did you guys get a R² value from something called an R² value from the linear regression?
You would have. Did we?
Yeah. I think this is the R² value. Could you please go up to show me the where we are getting it from? This is the linear
regression right here.
Up where we define the function. Yeah, here is the linear regression, and this is where they are from stats. And I believe the standard error should be R² here. I will confirm, but I'm pretty confident it is R².
Okay.
Okay. Awesome. So I just wanted to check on that one.
Yeah,
okay.
Keep it here. So that is. Could you please this line gradient intercept R value? Yeah. Actually, we have the R value. Okay, we have the R value. I will take the R value as well. R value is here.
Okay.
This is what
awesome.
Does.
So what that does is it basically tells us what percentage of this variance is actually explained by the linear regression for the particular value. So it becomes kind of important to understand how important that is. If I may throw one suggestion here, look at something called a QQ plot.
Mm-hmm.
So a QQ plot basically lets us know if the value is basically has the standard Gaussian distribution. But there's no major skew. So just a couple of questions from my end.
How do you spell that?
Okay. All right.
Can you go to chat and spell that?
Yeah, that was the gist of what we've done so far. Now we're interested in seeing an explanation for this relationship, or anything more. If we can look into any trend or any periodicity in our observations, that's kind of the next step.
From my side, so I think that it is the interesting thing is that as Celso also noted the first time, it is because Celso came up with the idea to compare veiling and flux one against the other outside the time domain. There, I don't see much periodicity here, but probably it is interesting to see why the veiling and the flux are proportional. I think we need a little bit input from Celso here.
Right.
Of course, my interpretation is that the higher the flux is, that means the material which hits the surface of the star is, of course, more energy. More energy, that means producing more, the veiling will be higher. Would you mind Celso chime in?
Yes. Well, that is the linear. I mean, when we are able to answer this question, we are able to write a paper.
Unmute.
Oh, somebody who is there? Oh, somebody.
So would you mind unmuting?
Oh, yeah. That's the problem when we mute microphone. I keep forgetting to bring it back. Yeah, but I mean, if if we can find the cause of it, we have a paper to write. So right now we are trying to determine what's going on and what the data can tell us. Basically, if I could use my tablet here to scribble something. Oh, I can't open that one. Let me see if I can find something here. Wait a second. There. So that's the paper. I highlight some points.
So this is from 2002. Okay, I have the same open.
Yeah. I just highlight the parts that had the helium or any information about helium. So the veiling at that time, I mean, this paper, I did the veiling part. Sylvia did most of the analysis. But at that time, I got 20 angstrom free of emission to calculate the veiling. Now we are using 10, so it's a little bit better. The steps are the same to find the chi-square, the best fit between deveiled, T-Tori, and template. We didn't do any analysis with the gravity. I would like to go to use the SME code and see if Lee Rottler and Ognian can get that code running. That would be good. So the helium line shows narrow component. You guys can see here, and broad component.
Yep.
The broader component is clearly red-shifted, while the narrow component is slightly asymmetric and centered, almost at the stellar rest frame. I don't know. Our case, it's not almost, it is there. I mean, as far as I remember, we didn't do a very good job in doing the radial velocity corrections we did now. And in all the cases that I check, the line center, the nominal line center, 5875.621, is dead centered in the top, in the peak emission of that line. And this asymmetry, I don't know. I would like to check that. I think this asymmetry is because of the broader component is kind of a fill-in the red emission of the line. I don't know yet. We have to invest some time in measure.
Really quickly, maybe so you could.
Yes.
So I read this paper from the Weiss, and so one of the things they noted is what they call a red noise. Is this the same thing?
Red noise?
Yeah, so they called it red noise. It's basically sort of a red noise that tends to show up in a lot of the flux data that kind of tends to mask some of this. Is that exact? Is this the same?
I don't know what red noise is. No, I don't know.
Okay.
Or could it be noise towards the red, longer wavelength? I don't know. Here's the lines.
Excuse me, Celso, for interrupting you. Would you mind explaining once again the broad and narrow, what did you say, noise or what
Oh, yeah. Let me see, the
broad and narrow components.
Yes. Let me go. Let me see if I can annotate here. Yes, I can. So let's take one of these helium line. Why is it not moving? It got frozen. Wait a minute. Okay. So, oh, because my tablet is not on. Without being power on, things can't work. Okay. So this helium line, I think this is even better here. So there are two components. One is kind of a broad, and the other one you can see probably beginning here.
Oh, I see.
And
okay.
Going up. I swear I'm not doing this. Okay, there you go. So then basically you have a combination of one kind of a broad and turbulent emission, and then you have another one that should be nicely symmetric. Now, the helium line it requires lots of energy to form this line, and the interpretation is, if you think that all this emission you see in H alpha, H beta, not so much calcium. This is something to be studied, but certainly in H alpha and H beta, all this emission comes from the accretion funnel. So think of the star with the disk around, magnetic field thread through the disk, stop the disk from falling in a Keplerian way towards the star, and then you start lifting this gas and then bring the gas to higher latitude. So in this process of traveling from the disk towards the star, so the gas increases its kinetic energy because it's falling down, potential energy converted to kinetic energy. It funnels, and then you have more collision, the gas heats up, and then these emissions are formed supposedly in this process. Okay. Now you might have also open field lines, magnetic field lines, that creates winds. So then you have the two situations going on at the same time. You have accretion towards the star, and you have wind going away from the star. So if you are observing that system, you see the two things as line features. So you see the gas falling down as a redshift blink or redshift feature in the line emission. And you see the gas coming out of the star, which means towards you, observer, as a blue shift feature in the line emission. So what Sylvia tried to do is say, okay, if I have consecutive data, can I see some variability in this blue emission or red emission that could be ascribed to either an expanding gas or accreting gas? So that's what she tried to do in this paper. So in the case of helium, since you need a lot of excitation, a lot of energy, so it has to be very much closer to the star. And now you have, I have to update myself with the literature because I haven't read anything the last few years, or 10 years, let's say. If the helium line is suggested to be formed before hitting the star, or in the star itself in the hot region, so-called post-shock region. So helium needs 50,000 Kelvin or a lot of ionization to be formed. But so people want, as far as I remember, 15 years ago, they would say, well, perhaps this broad component is formed in the region post-shock. So pre-shock, pre-hitting the star. And the narrow component is formed in the star itself, kind of is anchored in the star atmosphere. So one would be not so much turbulent and narrow and therefore symmetric, and the other one is broad and should be redshift. And the idea is, as you can see, this broad component has a peak that is more to the red, which indicates this broad component is turbulent because the winds goes in several hundred kilometers per second, and it's falling towards the star. That's why we see this line peaking in the red part of the spectra. So we have some red.
When you say Keplerian forces, you mean gravitational forces, right?
Yes, yes, because gravity is what essentially brings the gas to the star. But since the gas has also angular momentum, those two combine to give this Keplerian motion of the gas, of every particle of the gas, towards the star. But when it gets too close to the star at few stellar radii, the magnetic field becomes important enough and strong enough to halt this motion. And then the gas doesn't pass this shield, like Aurora Borealis expanded several times. And then the gas, which is partially ionized in the disk, gets stuck to the magnetic field lines. And then the gas that is not ionized gets also dragged along the rest of the gas towards the star. And then you have a gap between this region and the star itself.
The most important is the ionized, guys. This is where we have the solar wind, because we have the magnetic field, and if the gas is ionized, Keplerian forces are pulling it down, but then when it is close, it goes through the magnetic field, and it goes up, and then it goes to the other side.
It goes both ways. It goes, for instance, if we are, this star has some orientation, supposedly, which is almost pole on. So we have the disk like this, right? So it's almost like pole on, which means we see the action in one half of the hemisphere, but the thing is happening in the other side too.
I see.
Right?
Okay. So that means if the star is heads on, or how did you say when the axis is against us? How did you call this position of the star?
The dipolar field.
I mean, when the star is turning, this is the axle, and then when the axle points to our solar system.
Let me see if I can draw here. Let me see if I can draw here. Just a second. It's turning off again. Oh, I need to give some juice to my tablet. Just a second. There you go. Let me see if I can draw here. So we put a star. No, that's a bad one. Let's see. We have a star like this. Then so here's the stellar rotation. Stellar rotation axis. Go like this. So let's say the magnetic axis, something like this. Right? And so the dipole field could be something that goes like this. And then loop around, go back there. And then you have the same thing going on here, loop around.
This is the magnetic field, right?
Yes. And then you have a bunch, right? So you have all kind of things. So it goes, go. But here, I mean, the idea is, does it form a ring of hot material crashing down? Because see, the disk now, this magnetic field will pinch through the disk. So the disk is right here. So the magnetic field is pinched through the disk.
Would you mind trying to mute your microphone?
Yeah, there is a microphone in the background. So the magnetic field is pinching through the disk here, and the disk doesn't go further, right? And then the gas kind of lift up and then falls towards the star, and then you have this pre-shock region, the shock region, and the post-shock region in the star itself. Now, some people believe that in this region, open field lines also are responsible for initiate mass loss. So we have gas outflow here, and right here we have gas inflow. Now, if you are observing, now I can't. Oh, wait a second. Wait a second. No. Go back. So if you're observing the system from here, so that's your eyes. So your telescope is here. So if you're observing along this direction, so you are seeing this gas outflow with a blue shift feature. And the gas inflow as a red shift feature. Now, the star is rotating. So in half rotational period, this junk is going to be right here. Can you see that?
Yeah.
So if you were to draw again, it would be your rotation axis, your eyes would be here, and now this junk is right here. And then you have the same thing going on. And then you would see probably the features. With some different intensity. You could be able to see depending on the opacity of the disk, you could see something going on in the bottom part, right, in the southern hemisphere part as well, because now this hot region would be on view on the southern part. So if you have not such a opaque disk, you could be able to see something going on. So it's a complicated issue, and that's why people working in this field, they want to have as much data as possible, because then you can create a story. I mean, if you have the data, and if you can create a story that is consistent with the data, why not?
Yeah, this is an excellent explanation. So that means one possible, if we had the left case, I mean when the star is tilted, then we would definitely see periodicity in our observation.
That's correct. Okay, that's correct. When they start to find periodicity in classical territorial stars, these stars with a bunch of emission, they thought the periodicity would be due to this rotation. So if you have this model, they call this model of neutron star, because neutron star, they are magnetic, collapsed, and this beaming of X-rays associated with a neutron star, the model was brought to primitive sequence star to explain variability. But then yes, so if there is any periodicity in this blue shifted, in this blue shifted component or red shifted component, you could ascribe that to rotation. But it doesn't need to be necessarily associated with the stellar rotation, because these magnetic field lines might be delayed, might be, I mean, it's who knows what's going on with this field, if they are tilted, if they are pinched in a different way.
So it is not guaranteed that magnetic pole will coincide with the rotational pole.
No, it's not. I mean, in a perfect universe, we wanted the dipole field to be aligned with the rotational, but yeah.
Even in the Earth,
Earth is not. You have 10 degrees off, yeah, or 9 degrees, whatever.
Real quick question. So when we see that helium line that's somewhat shifted towards it's kind of wide and shifted over towards the red.
Yes.
That's the red shift of helium as it's falling into the star itself.
That is the interpretation I think Sylvia did in this paper. Yeah.
Okay.
Yeah. I think if I read it, if I go further a little bit, I can show that. Using two Gaussians. Okay, so Sylvia decomposed. Yeah, see that? So Sylvia, she decomposed the line in two Gaussians. So this is the red component. See, the peak of it is kind of off. The center part, the peak is off. And the smaller, the narrow emission component is kind of well-centered along the helium line. But again, we didn't have a nice radial velocity correction at that time. I didn't have the time to do what I did with you guys. We just want to have the results quickly. I was in the move to the United States. It was complicated. But when you add those two dash or traced lines, you match the profile. So this is something that I would like us to do. That would be the next step. So the next step for us would be to have all these 175 new data, make sure both Charnax and Philip have the flux for all of it, and then we compare flux, veiling, make sure we are in the same foot, and then we go decomposing the helium line. So we're gonna try to know as much as possible about one line, and use probably this paper as a reference for what's different from what we found in the past. So it is apparent broad components redshift, it's fit by a Gaussian. Yeah, she mentioned an asymmetry. I would like to see if there is an asymmetry in the narrow component, because this asymmetry could be due to bad fitting in the broad component. What? Who is speaking behind me? Oh, my iPad Pro is talking. There is a lady talking behind me. Looks like it goes. I found something on the web about @3. I don't like to see if there is any symmetry in an hour. Check it out. This is so weird. Which world we live on? Siri in the house. Let's see if there is anything else here. Correct equivalent width or correct line flux with veiling. She found a trend too.
So that's pretty much the same correlation.
Well, I was looking at the correlation here. The correct flux is wild. It goes to 5. Philip, can you check yours? It's less than that, right? Mine is less. Mine correlation flux and veiling similar to yours.
Can you see if is it going to 4, 3? I think it was up to 3 somewhere.
Yeah, so it went to 5, and so I think we were able to get data when the star was putting a lot of emission. And see if there is anything else here. Correlation. Oh, this is something she did was good. She tried to determine if the broader component and narrow component independently correlate with veiling. It's a way to say that. Yes?
Sorry for interrupting you. I'm looking at the graphic. Actually, in our case, it also went to 5.
Oh, it went to 5 too?
Outliers which went to 8.
Oh, went to 8?
Okay. That's we get exactly. I mean, your and our data is exactly the same.
Okay, all right. Okay, so that's makes me good. Okay.
Yeah.
Sounds good. So she correlates the broader component and narrow component, because if narrow component and broader component are both correlated with veiling, so you can say, okay, these lines are formed as a result of accretion, so they are dependent on accretion somehow. So the helium broad component, the funnel is formed in the funnel flow, and the helium narrow component in the post-shock region near the stellar surface, just to give the symmetry aspect of it.
So, sorry, post-shock, this is when the material falls on the surface through the magnetic line, right?
Yes. And before it's, because this material is falling 200 kilometers per second, 300 kilometers per second, depending from where it falls. So you have to go from 200 kilometers per second to 0, right? So you have a shock region in which you have to change the regime of the gas. So this post-shock region should be turbulent because you have this decelerating gas. And you should be able to see the wings of the helium line conform to that. The wings should go 200, 300 kilometers per second at the most, right? The extreme of the wings. Whereas the narrow component is pretty much, if it is narrow and symmetric, we could say, okay, that pretty much stuck to the star, which means it should be the post-shock region. So you have a pre and you have a post. And then for this line, you'd have the two regions kind of being mapped if you have enough data like we do. There's normalized variance. Yeah, composite origin coming partially from the accretion flow near the shock region, partially from the hot coronal wind. Coronal wind, according to this author, blue shift product component.
Blue shifted means it's that emission.
Yes.
Helium emission.
Yes.
Outside. Okay.
Yeah, but blue. Oh yeah. So the red shift, if there is a red shifted, is accretion. If it is blue shift, is hot wind. So I think you have to see if there was one of the data points I took in my notes. Let me see if I can find my notes here. One of the broad component was humongous, was really indecent. Let's see if I can find it. Because most of it, as far as I remember, I was keeping my eye on it when I was measuring. The broad component seems to be more to the red, which means we are talking about an accretion component. But I saw one that was humongous. Project log notes.
Alert from pages.
Grandpa or grandpa's out.
Sorry. Yeah, I call Grandpa later. Yeah, I have to find my notes. I will pass that information to you guys, but one of the notes were was one of the components was huge, and the narrow emission was not that great at all. It's small, so I have to figure that out. But and the rest is not so much in this paper. Berenstain, she went to this paper to find some information about the helium line. Excuse me, helium line. And that's Berenstain is the one who claims the hot wind for the helium line in case there is the broad component speaking the blue. So we have to I mean, when you guys start measuring the line flux, keep your eyes open for these details. Is there a broad component that is kind of a blue shifted? Obviously blue shifted. So take note of that. Write notes. Don't go in the automatic mode when you do these measurements. Keep your attention open.
Sophia Batalha.
I think I need to pick up my daughter. Just a second. Hello? Time to be picked up? Okay. All right. Okay, give me 10 minutes. Yeah. Because I'm in a conference here. No, she's not here. She's somewhere in Walnut Creek. Okay, bye. Sunday. All right. So, yeah, I'm sorry. I think I have to cut this.
Not a problem. Not a problem.
Yeah.
On my end, I'm still kind of grasp the field. I'll kind of go over. I posted some notes on this Weiss paper. I'm going to probably put together a couple more papers in terms of notes, just so I can, for my learning and just for anyone else to kind of quickly.
So I could go there and chip in and put information and things like that.
I'm sorry.
Could I go to your notes and put information or comment?
Yeah.
I sign my name
for the paper, and so yeah, anybody can edit it. Please do.
Okay.
If I'm not understanding some concepts, so I put a few brief notes. So I'll keep doing that, and on my end, I'm gonna go through some IDL tutorials, and we'll kind of go ahead and start jumping in as soon as I kind of get a handle on that.
Okay. Philip, I don't know if Sarah is still available or have the time, but if you could pass the IDL to her, I will leave the Zoom open and I go drive my daughter somewhere. That would be appreciated. I would appreciate that.
Also, is there some place I can get the access to all the papers?
Ooh. I can send the papers that I have to you. Yes. Yeah. Yeah.
Okay, that
Just
works.
give me few hours. I will be back and then I can do that. I have to do dinner too, you know. I have a busy Sunday. But I took a nap before, so that's good. And I'm looking for my IPA in a couple of hours.
Because do you still have the IDL installer that I sent in?
What I'll do is, Sarah, I'll just forward you what I have and kind of send you some instructions. I'll do that in a little bit.
Okay.
I actually am going for dinner in about 30 minutes.
Oh, my goodness. Okay, so can you guys communicate? I will leave Zoom open and I need to go.
Okay, all right. Bye.
All right, bye. Welcome, Sarah.
Bye.
Bye.